My name is Karol Havrila. I am a PhD student at the Department of Astronomy and Astrophysics in Comenius University in Slovakia, Bratislava. The topic of my presentation is micrometeorites or dust particle trajectories in the atmosphere from fireball fragmentation. In this research is part of my dissertation thesis. I am working on this research with my supervisor Juraj Tóth and my colleague Martin Baláž. Okay, one of the first questions we can ask is why is it important to focus on dust particles research? Because dust particles are very small, easily lost, often mixed with terrestrial particles, and very hard to find. So where is the motivation? The motivation for the research of dust particles is same to motivation for the larger fragments or meteorites. However, the big difference is in their total flux to the Earth's surface or Earth atmosphere. While the total flux of meteorites to the Earth's surface in a given interval is several 10 tons per year, the dust particles, the total flux to dust particles is several thousands or 10,000 tons per year. Then the dust particles represent the primary components of the total flux of the interplanetary material to the Earth. And next, in our study, we aim is to determine the dynamics of the dust particles and their concentration originating from the fragmentation of the large meteorites for their efficient collection during flying in the atmosphere. This is a little ambitious or after impact on the Earth's surface. Okay, in your case or in your research, we focus on the last phase of the body flies throughout the atmosphere, this dark phase of light. In the phase, the object does not emit radiation and we cannot visually observe him. Defining the position in the atmosphere, the shape of the trajectory and the impact area is based on the mathematical model. In our work or research, we focus on the aerodynamic model from Zeplecha. Here we can see the main part of the model, equation of motion, calculation of the trajectory total length, the change of geographical coordinates and in each integration step, and the current change of azimuth and zenith angle. For integration, we use classic numerical model methods Euler or Runge-Kutta for the order. Okay, we can the movement of the object is going on the atmosphere. In our work, we focus on two models of the atmosphere: international standard model of the atmosphere and extended model NRL MSIE 00 model. On the left picture, we can see standard or also Earth atmosphere model. It represents a general model of the atmosphere independent of geographical location and season. On the other side is an empirical analytical model. It combines data obtained from space probes, meteorological stratospheric balloons, and radar measurements. It should respect the presence of basic atoms and molecules in the atmosphere. It also specifies output values for solar activity, planetary magnetism, and geographical location. Next part of the aerodynamics model is the wind field. We prefer to working with the ERA5 meteorological database. The ERA5 database is the climate reanalyzers produced by ECMWF. Providing hourly data of many atmospheric parameters since 1979 to the present. Atmospheric data is analyzed on the regular latitude-longitude grids with the resolution, this resolution, with atmospheric parameters on 37 pressure levels. We can work with downloaded data in the Panoply program. or we can work efficiently with the RFI database in Python using PyAtmos library. On the other side, we have a real wind field data from meteorological stratospheric balloons are also available. And these balloons are launched from selected meteorological station 2 or 4 times daily. However, the disadvantage is the small number of stations that perform measurements using balloons. The data can be downloaded from the University of Wyoming website, and at the same time we can work with the database in Python using this library. An important part of the model is the drag coefficient, gamma. In our work, we have the option of several approaches to determine the value of the drag coefficient. We can work with constant value of the drag coefficient during the flight of the body. Also, on the left is the standard model, which is based on the tabulated function by Ceplecha. These values are determined for the symmetrical shape of the object and do not assume change in orientation. To the right is the approach that is described in my diploma thesis. The value of drag coefficient is obtained based on the object's real shape and its orientation. We obtain it for specific altitude in virtual wind tunnel using the micro-CFD program and 3D models of the, in our case, Košice meteorite. In the graphs on the right, we can see obtained shape of the curve of the drag coefficient depending on the altitude. Okay. In addition to defining the dynamic properties of object in the atmosphere, our primary aim is to determine the concentration of particles per unit volume in the atmosphere at a specific time or per unit area at impact on the Earth's surface. For this purpose, we need to know the total input mass of the fragments into the dark phase of light and probability of the fragments formation with selected or given mass. For this, we use the mass distribution of fragments, which uses the inverse cumulative distribution function, iCDF. It is defined as the distribution for the observed or recovered fragments. It represents a complementary cumulative number or vertical axis of fragments as a function of mass on a logarithmic scale. On the right, we can see the cumulative mass distribution for the Košice meteorite, where 218 found fragments are plotted. For using the cumulative mass distribution in practice or in our modeling, it's necessary to choose the suitable fitting function. In our work, we compare two approaches for selecting fitting function. We primarily worked with fitting on the right side because the area, this area of dust particle on the graph is significantly affected by selection effect, reason to the lower probability of finding the dust particle. Next, in our definition of particle concentration, we work with fragments of specific mass with a given number of generated clones. After obtaining their position in the atmosphere or on the Earth's surface, we evaluate the concentration using kernel density estimation or KDI, the statistical method, which estimates the probability density function on random variable. KDE replaces each position of our clones with a Gaussian shaped kernel, it's red color, and then obtains the resulting estimate for the density by adding up these Gaussians marked in blue color. And now look at the conversion of the probability density function to the particle concentration. We will by inspired illustrative image of the impact area. It's here, which is divided into a network of 6 × 6 bins. In the first step, at the input on the modeling, we define the total mass of fragments of specific mass, the number of generated clones, and the number of bins or our network, which divide our impact area. Yes. Based on the location of the individual impacts and the CADI function, we estimate the probability density of the fragment incidence in the individual bins. The total mass value, dividing, summing the probability density in all bins, we obtain a redistribution of the total mass into individual bins. Next, dividing the mass in individual bins by the mass of the model fragment, we obtain the number of particles per bin. And finally, dividing the obtained value of the number of particles in the bin by the size of the area of one bin, we can estimate the number of particles per square meter. This procedure is the same for determining the volume concentration in the atmosphere. Now, let's look at the program. It's my program that combines all the main joint models function. Micrometeorite trajectory name is a complex total with a user interface that we can see on the picture, and it is used for dynamic modeling of particle motion in the atmosphere, draws or shape of the trajectory, the impact areas, concentration, and more and more. The program includes a model of the dark phase of light, physical characteristic on the object, position of the object with deviation, and on the other hand, all the models mentioned, and possibility of particle rotation in time by gradual or random selection. And now I look at the modeling. We will focus on the case of the Košice meteorite. Sorry?
You have 2 minutes left.
Okay, thank you. Now let's look at the combines. We will focus on the case of the Košice meteorite, while we will analyze the area of the greatest brightness of the bolide. The greatest fragmentation is expected with the biggest proportion of the mass of the fragments format, with a total mass of 1,730 kilograms. We can see this fragmentation picture on the right, which represent the fragmentation model from article by Borovička. The fragmentation is defined by the formation of larger fragments in the interval of masses from this interval. We will illustrative increase of the mass range to also refer concentration of dust particle with a radius up to 400 micrometers. On the left, we can see the input parameters to the modeling. Here is the wind model, presents the real data from the nearest meteorological station, Poprad Ganovce, on the north of Slovakia. The wind field modified by 10 plus minus 10% for each clones, because the wind field change locally, and the place of the event is approximately 100 kilometers from this meteorological station. Okay, we will analyze the result. On the picture, we can see impact area for individual mass for all 5 model situation. Next, into 2 graphs describing the depends on geographical coordinates. We see the concentration for 10 grams fragments and 0.001 grams fragments at impact on the Earth's surface. The values are obtained using the KD function. Below we can see the output of our program, where is, let's see, more values, input mass, mass of particles, size of beam, and largest value for mass per beam, particle per square meter. And finally, let's look at volume concentration in the atmosphere. In the 2-3D projection, we see the geographical location and the altitudes of all clones. To the right is the state of the cloud after 1 minute after fragmentation. And on the right, we can see the cloud after 30 minutes of flight. Yes, and the last option, how to describe dynamics of particles in space, are animations. In the last two slides, we see an animation of moving particles for the first 10 minutes after fragmentation. To the right, we can see animation. The first show the first 5 minutes of fragments fly. The seconds, next 5 minutes of fragments fly. In the second animation, we can notice the gradual effect, the wind field, and the change in direction of the fragment. And that's all. Thank you for your attention.